So we learned the central limit theorem and the law of large numbers. I'm going to show you an example how to utilize them. So let's think about the income survey again. And suppose that the true randomly chosen persons, like single outcome or single person's outcomes, mean and standard deviations are given like this. Like we know the true distribution, and suppose we know the true distribution, and the mean is $50,000. Standard deviation is $10,000. And and but it doesn't mean we know the true distribution because we don't know the distribution of x. It is usually not normal, and usually it is positively skewed. That means there are extremely super rich, which is on the tail is pretty long on the right hand side. Okay, but so I don't care about the distribution of the true distribution, but I know their mean and standard deviation, right? And suppose that an economist surveys 100 people, simply just 100 people, and calculate their average. And then what we can do here is we can calculate the probability that this economist underestimates the average income by more than $3,000. How can you calculate that? So because we know the true mean is 50,000, so before doing the survey, we can tell what is the probability of underestimation. Okay, let me show you. This is basically what we want to do. We would like to calculate probability that the sample average of 100 survey respondents is less than $47,000. $47,000, and then we are going to apply the central limit theorem on x bar, assuming that x bar is the sample size is large enough, then x bar is approximately normal distribution with these parameters. The mean is the same as the single person's outcome, right? 50,000. So mean is easy. But the variance, instead of variance, I'm going to use standard deviation. You are going to see why. So standard deviation of this x bar, the sample average, is single person's standard deviation divided by the square root of n, sample size. Our sample size is 100. We do survey for 100 people. So the denominator must be radical of 100, which is 10. That's why I chose 100 as the sample size. So denominator is 10. That means the sample average has a standard deviation of only 1,000. It's 1/10 of the single person's standard deviation. That is the pattern, like the variability increases a lot when n increases. Like variability decreases when the sample size increases. Okay? And then anyhow, we learned, we know everything. We know x bar is normal distribution. We know x bar has a mean of 50,000, standard deviation of 1,000. So based on these three, how can we do that? We did a lot of practice on calculating this. Standardize x bar to this form, to standard normal distribution, right? So x bar subtract its mean and divide by its standard deviation, then you know this standardized random variable becomes a standard normal distribution z. This is easy, but what you have to remember is that you need to do the same standardization on the other side, on the counterpart of this inequality. So, $47,000 become 47,000 minus 5,000, 50,000 divided by 1,000. Okay, so you can calculate the right hand side, and left hand side does not need to be calculated. It's because it's standard normal distribution, random variable. And then right hand side simplifies to -3, which this probability z is smaller than -3 is a standard normal distribution probability. So you can use Excel, like you can use norm as dist normal distribution, standard distribution, -3, and cumulative is true. We are looking for cumulative distribution. That will give you 0.0013 blah 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 blah. So you may check the probability like this. Exactly, that's our result. And so this part is what we practiced in chapter 6. I did chapter 6 because we need to do that here and later, right? So if you think you need more exercise, you can go back and try them again. And this is a good example how we can utilize the central limit theorem and normal approximation to a sample average, right? Pretty interesting. But the problem is we have assumptions like this. We needed assumption that we need to know the single distribution's mean and the single distribution's standard deviation. We assume that and use them to calculate the sampling distribution's mean and standard deviation. Then from there, not a problem. But usually they are like single distributions, mean and standard deviations are not known. So we are going to use estimators. They are estimators. We can like think about estimation problem based on this idea. Already, it's interesting that the underestimation probability is really small. That's because of the low large number. 100 is a large number, so the error probability is already pretty small. Underestimation does not happen that much. Okay, so this is basic basis for standard deviation, like statistical estimation in the following chapter. Okay, so I will show you another interesting example. This is more economics rather than statistics. A good example of low large number, and this explains how insurance company makes money, how insurance company can survive. Okay, so let's think about car insurance, right? So suppose simply assume that you pay $500 premium a year for car insurance. But so your insurance will cover you when you have an accident. So suppose that if you have a car insurance, it will cost $3,000 to the insurance company. The insurance company pays you $3,000 when there is an accident. But it does not happen all the time. It happens only like with 10%, right? 10%, like this year, the probability that you have a car accident is 10%. If that happens, the insurance company pays you $3,000. But the other 90%, nothing happens, and you are just paying like 500, but nothing in return. So it goes like this. Suppose that X is a random variable. That is the profit the insurance company makes from you, right? So it is random because it depends on whether you have an accident or not, right? So the insurance company makes $500 with 90% because there was no accident. You only pay $500. But the problem is, if there is an accident, the company incurs a loss, which is a huge loss, like minus $2,500 with 10%. How can this company manage this loss, right? So if you scale it up, it means that the company should go bankrupt with 10%, right? That means in every 10 years, the company will go bankrupt. Impossible. Something is not right. Okay, so let me explain. I am going to think about a large number, 100. There are 100 insurance policy holders like you. So you and your friends and other people buy the same policy insurance, car insurance from the same company. And simply suppose that everyone has the same probability distribution, right? So 10% accident probability and with $3,000 reimbursement when insurance happens, like accident happens. And also assume that they are statistically independent, okay? And extending the notation, X subscript I denotes the profit from the ith policy holder. There are 100 policy like insurance policy holders, so like you can index them from 1 to 100, and ith person gives xi dollars uh, like as a random variable. So then to the company, what matters is the average, right? I'm going to think about X bar as the average profit from those 100 insurance policies. And the probability now, when you have 100 policy holders, well, like customers, the probability of an overall loss can be calculated like this. If the average profit is less than 0, that means the company is in deficit. Okay. How can we calculate that? Let's start from the single outcomes, single policies distribution. So we are going to find the mean and the variance of a single outcome, single person. Okay, this is the distribution. 90%, the company receives $500, but 10%, the company has to pay $300 back. So the net profit is minus 2,500. Like try yourself, calculate the mean and the variance based on the table first as an exercise. Okay, when you finished your calculus, I'm going to go to the next page. You can find the mean is $200. So to calculate the mean, you have to calculate probability weighted outcomes, just to remind you what we did in chapter 3. Probability weighted outcomes as a new column and sum them. That is your mean. And variance was a little more complicated. Based on the mean, you calculate the deviation and square the deviations and probability weighted deviations, sum them. That is the variance. Okay, so square deviation, square and multiply probability and sum, right? Just to remind you what we learned in chapter 4. Anyhow, the variance is a huge number, 810,000, right? So I intentionally made a number like this because the square root, the standard deviation, square root of the variance is 900, simply 900. So in the end, the mean is 200 and the standard deviation is 900. If you look at only one person has this mean and variance. But of course, we are looking at a company as a whole, like 100 customers together. Then, using the properties we learned earlier, the mean is the same. Mean of the average of 100, the expectation of the average of 100 is the same as the expectation of a single person, so it's 200. But the standard deviation of the average of 100 policyholders is the single person standard deviation divided by square root of 100, which is only 90, right? So we calculated the sample averages, mean and standard deviation, and then using those parameters, you can apply the center limit theorem and approximate the sample average to a normal distribution. Sample average is approximately normal distribution with this mean and this standard deviation, right? So, right, remember, we are looking for the probability of loss out of 100 customers. That probability is like this, like we are going to calculate this, but you know how to do it because it is a normal distribution with known parameters, right? That means you have to standardize the normal, non-standard normal random variable to this way. Again, the left-hand side is simply z. The right-hand side, 0, must be transformed in the same way. So 0 minus the mean divided by the standard deviation will give you minus 2.22. So probability the company makes a loss, incurs a loss, equals probability standard normal distribution smaller than minus 2.22. Let's find it out. Norm as dist minus, so I will just use 200 over 90 instead of minus 2.22. That was, it should be minus 2.2222 like infinitely. So I will use this form. And it is this probability, right? So 1.313% is the probability of loss, incurring a loss. It's only 1.3%. This is interesting because each person has 10% loss probability, right? So if you have only one person, the probability of loss is 10%. But by pooling 100 people, it becomes 1.3% only. So that is risk pooling. That means because even though one out of like one person may have like a loss, you need to pay $3,000 to one person, but most of the others will not. So the overall variability will be like compensated, like canceled out by each other. So risk will be pooled and canceled out by the low large numbers. 100 is a large number, so the risk is actually pretty small in the end to the company. So single person, I as a person, I have to handle all my risk by myself, which is really a huge risk. But to the insurance company, it goes away. That's economics interpretation of how insurance company works and how it works, right? So now, what happens if you have 10,000 people together? You are pulling more people together, like Geico, State Farm. I don't know how many policies they sell, but it should be more than 10,000. So let's think about this. I chose 10,000 because its square root is simply 100. And this is your practice, so try it by yourself to the algebra. Right? It requires multiple steps. Okay, so the idea is we are going to calculate this probability, and we know x bar is the random variable here, which is approximately normal distribution with mean and variance based on these information, right? So first, you calculate the mean and standard deviation. Mean is the same, which is simple, but standard deviation requires divided by square root of 10,000. So single outcomes, single variable standard deviation divided by the square root of the sample size, which is now 9. Single person, my risk was 900, but to the insurance company who have 10,000 people, it's only 9, 100 times lower. So anyhow, the X bar is a normal distribution, approximately normal distribution with 209 squared. And then we get this, right? So standardization as usual. Of course, it goes like left hand side is z, but the right hand side needs a little algebra, which is now minus 22.22. Da 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 da, like infinitely. 2 goes infinity. Uh, and then if you find it from normal distribution, like it, this is what we are calculating. It is a super small number. Hard to find non-zero number here. Surprising. I don't know. I don't know how many zeros you have to go to find. So basically the risk does not exist, right? It's surprising. I was surprised too. I thought we can find some non-zero number. Anyhow, you see, like 0 point, these many zeros. Risk is basically does not exist. Okay, the risk disappears because you are pulling many people. It's a large number, so it's a power of the large number. Um, so you can learn interesting results from the law of large number. Okay, some additional topic is comparison with binomial distribution. Actually, they are pretty similar in the sense that you think about multiple observations at the same time, right? Sampling distribution is about the average of multiple outcomes, and the binomial distribution is also about the sum of the count of multiple binary experiments. So actually, they are similar. Binomial distribution, two differences. Binomial distribution requires single outcome is binary, and second, it is looking at the sum count instead of the average. But otherwise, they are basically the same, right? So if you think about binary random variable xi, and if you think about the sum, that is binomial distribution. But if you think about average, then it converges to a normal distribution by the central limit theorem, right? So they are related. They are pretty much related, but it depends on what you are looking at. In some cases, the average is more useful, and in some cases, you are looking at the sum. But also, average and the sum are pretty much the same thing because whether you divide by n or not. So if you know the sum, then you can simply divide by n and get the average. So they are also pretty close to each other. Last example, like overbooking example. We learned overbooking example in the binomial case. But at that time, we used pretty simple numbers because we did not want to go like if we use like 400 as the number of reservations, then it is nearly like very difficult to apply the formula, right? Formula does not work well in here because it will be very close to zero. So now we can handle a larger number. Say the capacity of the flight is 370, but the airline accepted overbooking, so the total number of reservations is 400, right? 30 more reservations are made, and the probability of cancellation is 10% again. We would like to calculate the probability of 30 or fewer reservations, like if overbooking causes a problem. If there are more like ticket holders come to get on the flight, okay? So then two possible cases. Earlier, we used binomial distribution. Y is the number of cancellations. Then we use binomial distribution with parameter 410%, right? You can calculate binomial distribution probability less than 30 or less than or equal to 30. So you can count this. You can calculate probability up to 30 out of 400 sample size when the success probability is 10%. You are calculating true cumulative distribution. It is 5.239%. Okay, so we can calculate this probability based on the binomial distribution. But this is not an approximation. We are using the binary random variable, so it's exactly 5.239%. But we may also use approximation to normal, right? So earlier we were interested in the probability of the number of cancellations less than 30. But instead of the number of cancellations, if you divide it by the sample size, the left-hand side is average. You are changing the number of cancellations to the percentage of cancellation, right? The average is, remember, average for a binary distribution is probability of success. So this average is actually probability of cancellation. That's what we learned in chapter 5. So instead of calculating probability that the number of cancellation is 30 or smaller, I'm going to calculate the cancellation rate is less than 0.75. They are basically the same thing. When the rate of probability of percentage of cancellation is less than this, then you are going to get less than 30 cancellations. Then how can you approximate this to normal? Yes, we are going to approximate this to normal. To do that, you need to calculate the mean and the variance for a single reservation, which we did in the earlier chapter, right? So the mean of a binary single reservation binary variable is the probability of success, which is 0.1. We learned it. And the variance of a binary random variable is probability of success times probability of failure, which is 0.1 times 0.9, 0.09. And standard deviation is square root of that, so 0.3. Right? You remember? It's from chapter 5, right? So when you have single binary outcome, the mean and the variance are pretty easy to calculate. Based on them, we are going to obtain the mean and the variance for the sample average when you have 400 reservations instead of a single reservation. When you have 400 reservations, the mean does not change, but the standard deviation changes like this. So you have to divide the original standard deviation by square root of 400. Then it is 0.015. Okay, so we use the mean and the standard deviation for the sample average like this, and then this probability can be standardized using those parameters, and you get probability smaller than standard deviation smaller than minus 1.667 approximately. Then you get another number here. Okay, and then why are they different? So the first, we calculated the same probability using two different methods. One is binomial distribution, and the other is based on the central limit theorem normal approximation. They are different. What is correct? Binomial distribution is correct in this case because normal distribution is an approximation, but binomial distribution is not. It's a correct probability, but we are approximating the binomial distribution to a normal distribution. So the difference is the approximation error that happens, like which is less than 1%, okay, about 0.5% point. but this approximation error will decrease if the number of reservations was larger, right? It depends on the sample size, but it's still an approximation. Okay. Okay, this is the end of chapter 6, and I hope you enjoy this. And I like maybe this is what you expected from a statistics course now. So we are going to use these fundamental powerful theorems to learn estimation and hypothesis testing. Okay, thank you for watching. See you in the next chapter. Bye.